Okay. So, come to the solution of this problem. So, this is just now we have given that problem. So, following parameters are given: r is equal to 1.5 centimeter, that is 0.015 meter, p is equal to 740 mm, this is given, T 27 degrees Celsius. We know this formula, delta is equal to, again and again not writing the equation, these are known to you. So, 0.392 p upon 273 plus t. So, p is 740 and t is 27. So, it is delta is equal to 0.967. Now, also given that dq is equal to 4.8, because equilateral is spaced for 4.8 meter. So, d equal will be 4.8 meter. m0 is given 0.85, g0 is given that 21.1 kb RMS per centimeter. So, this can be converted to 2.11 10 to the power 6 volt per meter, it has been converted to volt, right. We know disruptive critical voltage RMS, this formula we have also derived. So, V0 is equal to G0, then M0 R delta ln dq upon R volts, right. This formula is also given. So, G0 is given, M0 R delta dq R all are known. So, you substitute here, right. If you substitute, then V0 will be 2.11 10 to the power 6 into 0.85 into 0.015 into 0.967 ln 4.8 by 0.015 volt. So, V0 is equal to 150.06 kV, right. This one first you compute using this formula, that is your disruptive critical voltage V0, right. Next is for local, now this thing, for two things are given, one I am calling as a local corona, another I am calling general corona. Again this is a question to you, what is local corona and what is general corona, right. This is a question to you. So, you will write 1 or 2 line answer and will send it to me, right. So, for local corona, look at the parameters carefully, everything, then you will answer. MV is 0.72, we know visual critical voltage RMS, this formula is known to us, VB is equal to G0 MV R delta in bracket 1 plus 0.0301 by root over this thing R delta into ln dq upon R. All parameters are given, it is we converted to volt per meter. So, VB 2.11 into 10 to the power 6 into MV 0.72, R 0.015, delta we have computed 0.967 into 1 plus 0.0301 divided by R delta 0.015 into 0.967, and this is ln 4.8 upon 0.015. So, VB actually your visual critical voltage is coming 158.87 kV, right. But remember this is all RMS value, bracket I am writing, here also I have written, here also I have written, right. This is your 158.87 kV. Now, in general corona MV is equal to 0.82, right. Look, for local corona it was 0.72 and for general corona 0.82. From that you will try to tell me this to answer, what is this, what is local corona, what is general corona, right. No need to use further because all are directly proportional. So, just use that ratio thing, whatever you have got 158.87, it is VB general corona 158.87, but here MV is 0.82. So, it is 0.82 divided by here local corona 0.72. So, divided by 0.72 is equal to 180.93 kV, right. So, actual operating voltage to neutral actually 220 upon root 3. So, 127 kV, right, because line voltage was 220 kV. So, 225 root 3 means line to neutral for 120, so which is less than VB, and there is no corona, because this voltage, right, less than your what you call that your VB, the visual disruptive voltage, right, visual critical voltage rather, right. So, that means there is no corona. So, there will be a question, then giving this parameter you have to predict from that this thing whether corona will happen or not, right. So, next is example 3. Determine the corona loss of a 3 phase 220 kV 50 hertz and 200 kilometer long transmission line of 3 conductors, each of radius 1 centimeter and spaced 5 meter apart in an equilateral triangle formation. That means, again dq will be 5 meter, right. The air temperature is 30 degrees Celsius and the atmospheric pressure is 760 millimeter of mercury. The irregularity factor is 0.85, right. So, these are the things what these every time I am taking equilateral triangle, right, that is conductors of space. Now, a numerical I am giving, just recall that if you take this horizontal spacing, that 5 that is horizontal spacing means that between AB say 5, between BC 5 and AC is 10, right. B is the middle conductor between A and C, and between A and B 5, B and C 5, and A and C will be 10, then, right. You will try to find out with all other parameters remain same what will be the corona loss and compare whatever we are getting as. This is an numerical to you, you will solve it, right. Now, from equation 44, this is your Pick's formula, that PC is equal to 244 upon delta in bracket A plus 25 into Vn minus V0 square into root over R upon capital D into 10 to the minus 5 kilowatt per kilometer per phase, right. Now, F is given 50 hertz, delta you have to compute because it is given, delta is known, right, this is known 0.392 P upon 273 plus T, P is given 760, that is atmospheric pressure, right, and T is 30 degrees Celsius. So, it is coming 0.983. So, now R is equal to given 1 centimeter, so 0.01 meter, and D will be 5 meter, D or DEQ same because it is equilaterally spaced 5 meter apart, right. So, D it is equal to, you can write if you have a this thing, D actually is equal to DEQ, this same thing, right. I have written D here, right. So, that means based on that you calculate V0 is equal to 3 into 10 to the power 6 by this formula is known into R into delta into M0 into ln D upon R. So, 3 into 10 to the power 6 upon root 2, R is 0.01, delta we have computed 0.983 and M0 is 0.85 and D is 5, ln 5 or R is 0.01, so it is volts. If you compute this one, you will get V0 is equal to 110.5 kV RMS value, this is RMS value. Now, Vn is equal to 220 upon root 3 kV, that is 127 kV, right. So, that means this one your this thing higher than this one. Now, PC will be 244 upon 0.983, F is 50 hertz. So, 50 plus 25 the this your Pick's corona loss formula, it is A plus 25, A plus 25. So, it is 50 plus 25 into 127 minus 110.15 square, 110 point, it is actually 110.5 not 15, it is 5 actually 110.5 square, right. So, please when you will check it, no, please check this calculation correct or not, because just repeating that all these numericals actually all are your calculated by me only, right. So, if you find any error in calculation anything, you are always welcome, just that you let me know that sir this is that calculation error, and I will appreciate that, right, because all these calculations actually done by me only, not by my student. I have done everything of my own, all these things. So, you just let me know that if there is any error in any calculation error, then I will rectify that, right. So, into root over your 0.01 by your 5 into 10 to the power minus 5, and it is actually this Pick's formula, this one is actually kilowatt per kilometer per phase, but line length is 200 kilometer, that is why it is multiplied by 200. So, therefore, it is kilowatt per phase. So, per kilometer will not be there because it is multiplied by 200. If you do so, so PC will be 472.73 kilowatt per phase, therefore, it is per phase. So, there are 3 phases. So, total corona loss will be 3 into 472.73, therefore, it is 1418.19 kilowatt, right. Some numericals for every chapter as much as possible I am showing you, such that you can, it will be easy for you to study. Next is that example 4. Here calculate the disruptive critical voltage for a 3-phase line with conductors of radius 1 centimeter and spaced symmetrically 4 meter apart, right. So, in this case from equation 36b, the disruptive critical voltage formula is that V0 3 into 10 to the power 6 upon root 2, then R into ln dq upon R volts per meter, right. So, R is equal to 1 centimeter, therefore, 0.01 meter, and DEQ 4 meter, it is given symmetrically 4 meter apart, right. Therefore, V0 is equal to 3 into 10 to the power 6 upon root 2 into 0.01 into ln 4 upon 0.01. If you calculate this, V0 will be your 127.1 kilovolt, that is line to neutral voltage. Therefore, line to line disruptive critical voltage to root 3 into 127.1 is equal to 220.14 kV, right. So, this is that line to line disruptive critical voltage. Next one is, so I think this numericals will make your whatever theories we have seen, this numericals will help you to understand this, right. Next is this example. This is example 5. A 220 kV 3 phase transmission line with conductor radius 1.3 centimeter is built so that corona takes place if the line voltage exceeds 260 kV RMS. Find the spacing between the conductors, right. So, you have to find out the spacing here between the conductors. Now, disruptive critical voltage, it is RMS value, this thing your what you call that your if the line voltage exceed this one, right, 260 kV RMS. So, find the spacing between the conductors. Therefore, disruptive critical voltage V0 actually is equal to V RMS, that is 260 by root 3 kV, that is 150.11 kV, right. So, it is your what you call, it was given if the line voltage was given. So, we are making this one as a phase voltage. So, because all calculations we are making based on the phase voltage. So, it is 260 by root 3 kV, so 150.11 kV. Therefore, from equation 40, V0 is equal to 3 into 10 to the power 6 upon root 2, then R into delta into M0 into ln dq upon R volts per phase, right. Now, assuming, now here you have to assume something, assuming delta is equal to 1. If these parameters are not given, for example, that air density factor delta or m, you assume they are unity. If it is not given, you have to, if it is not given, means you have to assume unity, even it is not mentioned in the question, you have to assume that it is unity, right. That means, I am writing assume that delta is equal to 1 and m0 is equal to 1, that is for smooth conductor, right. Therefore, R is equal to given that your 1.3 centimeter, that is equal to your 0.013 meter, and V0 is this one, right, 150.11 kV. So, it is 150.11 kV is equal to 150.11 that was 3 volts, we are converting into volts. Therefore, this 150.11 into 10 to the power 3, this is V0 is equal to 3 into 10 to the power 6 upon root 2, delta and m both are 1. So, delta 1 into R 0.013 into ln d upon 0.0013. If you solve this equation, it will give you d is equal to, I think exactly 3 meter it will give, you should check, right. So, that has been asked actually to find the spacing between the conductors. So, this d is equal to 3 meters, right. Next, another example, first theory and then example, right. Now, example 6, in this case that a 3 phase equilateral transmission line has a total corona loss of 50 or 55 kilowatt, right, and 110 kV and 55 kilowatt at 110 kV and 100 kilowatt at 114 kV. That means, it is given that when corona loss is 55, voltage is 110 kV, and when it is 100 kilowatt corona loss, voltage at that time it was 114 kV. Then what is the disruptive critical voltage between lines, right, and next what is the corona loss at 120 kV. These are the things you have to find out, right. So, power loss due to corona for 3 phase is given by, this is your Pick's formula, Pc is equal to 3 into 244 upon delta A plus 25 root over R by D into Vn minus V0 square into 10 to the power minus 5 kilowatt per kilometer, right. Now, this earlier it was kilowatt per phase per kilometer, but here you look, we have multiplied this one by 3, here we have multiplied by 3 means that is why per phase is not there, because to this whatever Pick's formula it was per phase, but we have multiplied it by 3. So, it is given kilowatt per kilometer, right. Now, taking delta, F, R and D all are constant, because delta is constant, F is a constant, R is constant, D is constant, so all are constant parameters, right. Therefore, you can write that corona loss Pc is proportional to that Vn minus V0 whole square, right. That means Pc proportional to Vn minus V0 whole square, because all are constant, other parameters are constant, delta A, R and D all are constant. That means, in general we can write Pc is equal to k into Vn minus V0 square. Say this is equation 1. Now, it is given that when Pc is equal to 55, Vn actually 110 by root 3 kV, because everything you have to take your what you call that line to neutral voltage, right. So, when if nothing is mentioned, then you have to assume they are line to line voltage if nothing is mentioned, right. So, that is why Vn is taken 110 by root 3, that is line to neutral voltage, because as it is not mentioned in the problem, you have to assume that they are line to line voltage, right. So, when Pc is equal to 55 kilowatt, so Vn is equal to 100 kV, it was line to line. So, that means you make it is line to neutral, that is 110 by root 3 kV, right. That means you can write 55 is equal to k into 100 by root 3 minus V0 square. This is equation 1. This is equation 1, right. Similarly, when Pc is equal to 100 kilowatt, Vn is given 114 kV, that is line to line. So, 114 by root 3. So, line to neutral you make it, and again you can see using same equation you can write 100 is equal to k into 114 by root 3 minus V0 whole square. This is equation, this is 1, this is equation 2, right. Now, divide you equation 1, this equation and this you can divide, k and k will be cancelled, right. So, dividing equation 1 by equation 2 you will get 55 by 100 is equal to 100 by root 110 by root 3 minus V0 whole square divided by 114 by root 3 minus V0 whole square, or this equation left hand side we are writing, you can write this will be 63.5 minus V0 and this will be 65.8 minus V0 whole square is equal to 0.55. If you solve this one, you will get that V0 is equal to 57 kV, right. So, this is square, so square root is 0.74, after that you solve it, you will get 57 kV, right. Therefore, in the second case we know W is equal to k 120 by root 3 minus V0 square, right. This one actually known to us, right. This formula is known to us, and second case it is asked that if the voltage is 120 kV, what is the corona loss. So, in this has been converted, 120 kV is converted to line to neutral. So, 120 by root 3 minus V0 square, and it is in bracket I am writing for you Vn is equal to 120 upon root 3 kV, this is Vn, right. So, dividing equation 3 by equation 1, this is equation 3, divide by equation 1, it will become W by 55 is equal to 120 by root 3 minus V0 square divided by 110 by root 3 minus V0 square, right. But V0 we have computed 57 kV, therefore, W is equal to from this equation 55 into 120 upon root 3 is 69.28 minus 57 whole square, right, divided by 63.5 minus 57 whole square, right. If you solve this, W actually will become 196.3 kilowatt, right. Therefore, line to line disruptive critical voltage will be root 3 V0, because we have got no V0 is equal to your 57 kV, this is line to neutral, this is line to neutral computation, then line to line disruptive critical voltage will be root 3 into V0, that is root 3 into 57. So, 98.72 kV, right. So, I hope one more example for you. So, I hope this is the examples are easier, quite easier, right. Now, this is the last example for corona, example 7. A 220 kV 50 Hz 3-phase transmission line consists of 1.4 centimeter radius conductors spaced 3 meter apart in equilateral triangle formation. If the temperature is 27 degrees Celsius and the atmospheric pressure say 750 mm of mercury, M0 is given 0.80, you have to find out the corona loss. So, disruptive critical voltage, this formula we know, it is V0 is equal to Vrms is equal to 3 into 10 to the power 6 upon root 2 into R into delta into M0 into ln dEq upon R, volt per phase, right. R is given 1.4 centimeter, that is 0.014 meter, M0 is given 0.80, P is 750 mm of mercury. Therefore, delta you calculate, this formula is known to us, this formula is known to us. So, delta is equal to 0.392 into 750, the P divided by 270 plus T, T is 27 is equal to 0.98, and DEQ is given 3 meter, DEQ is given, right. So, with this V0 is equal to Vrms is equal to 3 into 10 to the power 6 upon root 2 into 0.014 into 0.98 into 0.80 into ln 3 upon 0.044 volt per phase. You substitute all the parameters, equations are known, just you have to keep it in your mind for the exam purpose, you have to keep it in your mind. Therefore, V0 actually 124.97 kilovolt per phase, right. Therefore, corona loss using Pick's formula. So, Pc is equal to 244 upon delta into F plus 25 root over R by D, right, into Vn minus V0 square into 10 to the power minus 5 kilowatt per kilometer per phase, right. That means, Pc is equal to 244 upon delta, delta is given 0.98, we have computed it, right. F is 50 hertz, so 50 plus 25 into root over R by D 0.014 by 3 to the power half, I am writing root over, then into your 220 upon root 3, right. So, every time you have to convert it to line to neutral voltage, right, minus 124.97 whole square, because we got this one per phase 124.9 into 10 to the power minus 5, it is kilowatt kilometer per phase, not writing again here, but here I have written. So, Pc is equal to 0.0534 your kilowatt per kilometer per phase, right. If you suppose line is 100 kilometer long, then it will be 5.34 kilowatt per phase, right. If it is a 3 phase line, then it will be your 16.02 I think kilowatt per phase. So, for 100 kilometer long line, that your what you call that corona loss is quite high. So, all these things from the design point of view, for when practicing engineers, so in the design a transmission line, they consider all the factors, right, even most worst, including the worst case condition. Based on that, they just design the transmission line. So, with this we will finish corona, right. So, this chapter is over, the corona loss is over. Next, now next thing is that analysis of sag and tension. So, just before starting the sag and tension of the transmission line, when sag and tension will be over, next we will go for distribution system your load flow. So, which is not Newton Raphson or Gauss Seidel, two methods only I will try to tell you, and you will find it will be very effective. For example, that because nowadays because of renewable sources or dispatchable or non-dispatchable DGs, that distribution system getting more and more important. So, after this sag and tension, you will find it is basically your analysis sag and analysis of the transmission line, mathematics are involved here, and after that you will find the distribution load flow capacitor, then little bit voltage stability, load frequency control, and of course, unit commitment. So, all these topics are of highly interesting. So, this sag and tension also you will find very interesting topic when we will come into the mathematics, and you will see how is it, right. So, analysis of sag and tension, right. This is a quite known thing to you, right. So, particularly you have seen that long transmission line, when it is connected between your two towers, right. In summer you will find that it is a catenary shape, that that conductor is taking something like your what you call your bow type of shape, we call catenary shape. So, it is not it never be horizontal, right, because of its weights and wind pressure, right. So, we have to find out the maximum sag. In summer you can find, due to as the temperature is very high, that means sag may increase, and in winter temperature is low, the sag will be less. So, we will see that sag and tension, including the effect of your snow covered conductor, and as well as your what you call that temperature variation. So, just have a look for different type of conductor, your what you call tower in the plain areas or tower crossing the river, or not at the same altitude, or in the hilly area also not at the same altitude. So, what should be the sag and tension? So, it is a little bit longer chapter. So, just see this initially little bit of introduction, and then we will come to the mathematics, right. So, first is some introduction. So, analysis of sag and tension of conductor, that is an important consideration in overhead transmission as well as distribution line design, both transmission as well as distribution, but transmission is more important, right, more important. The continuity and quality of electric service depend on largely on whether the conductors have been properly installed, right. Thus, a design engineer must determine in advance the amount of sag and tension to be given to the conductor at a given temperature, maximum wind and possible ice loading. All these things you have to consider. One is that maximum temperature. I mean, when they design this, I mean try to compute sag and tension, they consider the extreme cases, that is your temperature, maximum wind and possible your ice loading, all these things they consider, right. And in order to specify the tension to be used in stringing the line conductors, the values of sag and tension in summer and winter condition must be known, because I told you in summer that expansion that of conductor will be more. So, sag will be more, we will come to see that, and winter it will be less, right. So, excessive tension sometimes may cause mechanical failure of the conductor itself, because conductor tension contributes to the mechanical load on structures at the angles in the line and at dead ends, right. So, so many issues are there, so many your what you call mechanical things you have to consider, particularly for connect your what you call installing conductors at both the towers, right. And particularly when you are using say vertical configuration, you have to be very careful, right. But horizontal configuration is okay, but vertical configuration because sag will be there. So, one has to be very careful that it should be uniformly placed, right, all the 3 phase conductors. So, the main features in the design and your stringing the conductors on the support are, I mean the design, and you are basically you have to connect the your how to conductors on the both the towers, right. So, first thing is conductor load per unit length, that means conductor itself you know it will be very you have seen the distance between the towers up to 100 meters or 200 meters, it depends you know your what type of voltage level you are using and the tower height, altitude, right. So, in that case the conductor load per unit conductor is very heavy conductor, right. So, that also you have to consider. So, conductor load per unit length. Secondly, conductor tension also you have to consider, the span, that is distance between the two support, two tower you have to consider, and temperature of course you have to consider. So, all these factors you have to consider. Next is for determining the conductor load, the factors that need to be considered, that weight of the conductor itself, that you have first thing, then weight of ice or snow clinging to conductor, particularly in the hilly areas, there is a possibility which will happen that ice or snow formation on the conductor. So, that also you have to consider, and wind blowing against conductor, this also you have to consider. Later we will see for mathematical derivation this wind blowing against conductor, right. Therefore, the maximum effective weight of the conductor is the vector sum of the vertical weight of the conductor, that we will see at the time of mathematical derivation, and the horizontal wind pressure, both we have to consider. It is extremely important to include most adverse condition, I mean we have to consider the adverse scenario. From the design point of view, it is considered that the wind is blowing at right angles at the line, right, and to act against your projected area of the conductor, which includes the projected area of ice or snow that may be clinging to it. I mean everything we have to consider, and whenever we are this thing that the wind is blowing at right angles of the line and to act against the projected area of the conductors. I mean just to consider the extreme cases, we have to consider all these conditions. So, when you will go for mathematical derivation, we will come to this, right. So, from the practical point of view, economic design dictates the following. One is sag of conductor should be minimum to refrain from extra pole height. I mean, if your sag is low, then tower height or pole height will be less, but if sag is more, then tower height will be more, because you need some minimum ground clearance, right. Then sufficient clearance, that is the thing, second line, sufficient clearance above ground level. Then third point is to avoid providing excessive horizontal spacing between conductors to prevent them swinging together in mid span, right. I mean, you have to avoid providing excessive horizontal spacing between conductors to prevent them swinging together in mid span. I mean, these are the things you have to consider. Another point is that the sag of conductor decreases, right, because its tension pulls the conductor up, because when you are connecting the conductors on the both the towers, right. So, it tensions actually pulls conductor up, but at the same time the tension elongates the conductor from your elastic stretching, which tends to relieve tension and sag increases, right. Very interesting, right. Look, the sag of the conductor decreases because the tensions pull the conductor up, that is fine, right, but at the same time tension elongates the conductor from elastic stretching, which leads to relieve tension and sag increases. These are the factors later we will see mathematically, because we have to consider also, right. We have to consider your what you call that conductor tension, actual cross section, everything we have to consider. So, thank you very much, again we will be back.